Last class we have been discussing about torque. Now we are going to discuss torque on a sliding block. Let us consider a small block of mass m. This is a small block, has got mass m. It is sliding along the positive x direction. It is sliding freely. That means there is no friction. Initially we are imagining there is no friction. It is sliding freely along the x direction with velocity v. And we are going to consider an origin B. From the origin B, the position vector of this particular mass is RB. So the angular momentum about the origin B, if you calculate, LB will be equal to mass m into position vector cross velocity. So mRB cross V will be the angular momentum about the origin B. RB we can resolve along the perpendicular and parallel component. Parallel component will not contribute because when you take the cross product along V, it will be 0. So only the perpendicular component of RBs need to be considered. That will be equal to L in magnitude. So instead of RB we can write L. So MLV. V is equal to VI because only the x direction we need to consider. So MLV, that is the magnitude of the angular momentum about the origin B, and its direction is perpendicular to both RB and V. So that will be along the Z direction because both these constitute along the XY plane. Perpendicular to that you have the angular momentum LB, which is in the positive Z direction. This is LB. Now when the block is sliding freely, this is the situation. But in the real situation, there is friction. So we need to consider the friction also when the block is moving. So due to friction, this block will slow down. The frictional force F is equal to minus F into I. The frictional force is trying to reduce the velocity. Frictional force acts in the opposite direction. So this is the frictional force acting in the opposite direction of motion. Motion is along the positive x direction. So frictional force will be along the negative x direction. So you have F is equal to minus Fi. Now let us find out what is the torque on the block about the origin B. The torque we have discussed in the previous class. It is equal to R cross F is the torque. About origin we have considered. So the torque tau B will be RB cross F, that is equal to RB is equal to L. The magnitude of RB becomes L because only the perpendicular component we need consider L into F because frictional force is minus Fi and the direction of the torque is perpendicular to both RB and F. F is in the negative x direction. Minus I means negative x direction. So torque will be LF into minus K. It is in the negative Z direction. So the angular momentum is along the positive Z direction. Torque is along the negative Z direction. This is the direction of the torque tau B about the origin B. As the block is slowing down due to friction, the block slows down. Angular momentum LB remains along the positive Z direction. The direction of angular momentum remains along LB itself, but its magnitude will decrease. Due to the frictional force, the angular momentum will decrease. The change in angular momentum about origin LB is delta LB. Delta LB is the change in the angular momentum. The change is taking place in the opposite direction because it is decreasing. The direction of change of angular momentum is along the negative Z direction. It is the same as the direction of the torque tau B. This is angular momentum LB along the positive Z direction. The change delta LB along the negative Z direction. Due to this change, the angular momentum decreases. The angular momentum at time t is LB. After a time delta t, it has decreased by delta LB and it becomes LB of t plus delta t. So the magnitude, you can see initially the magnitude of this much. Now after a time delta t, the magnitude has decreased to this much. Torque is rate of change of angular momentum. We have discussed this in the previous class. And in general, torque and change in angular momentum are always parallel. This is the change in angular momentum and torque is along this direction. You have seen the previous figure. So I can write delta LB, the change in angular momentum, is equal to ml into change in velocity delta v into k. Delta v is less than 0 because it is decreasing. So I can divide delta LB by delta t. Here it will be ml delta v by delta t into k. And when delta t is very small, you take the limiting condition. When delta t tends to 0, you apply to this equation, you get rate of change of angular momentum d by dt of LB is equal to ml rate of change of velocity into k. dv by dt is our acceleration. So m dv by dt will be the force. Here the force is equal to the frictional force, which is equal to, its magnitude is minus f. Frictional force in the opposite direction. So I can write dlb by dt is equal to L I have taken. Instead of m dv by dt minus f I can write into k. So this is equal to the torque tau b. So the torque and angular momentum L depend on choice of origin. Angular momentum we have discussed in the previous class also, and it is depending upon when the origin changes, the quantity also changes. So when you are discussing angular momentum and torque, you should have to discuss it about the same origin to apply this relation. If you are finding out torque of a particular torque at a particular origin, angular momentum or at that origin itself should be considered. Only then we can apply this condition, because we can consider different origins and find out the values. Now we are seeing that the angular momentum of the block is changed only in magnitude. The angular momentum, initially it was this much, now it has decreased. So the magnitude has changed, but the direction is remaining the same. Direction has not changed.